All right, so here we're going to work through the first practice quiz posted for the first ME-410 quiz. So let's get started at the beginning with the conceptual questions. All right, so our first question is looking at this vacuum insulated flask. We kind of talked about an example like this early in the course in the first couple classes. So one important feature that makes this flask work is that there's a vacuum gap between the inner wall and the outer wall, and if that is properly evacuated, the only significant mechanism of heat transfer there is radiation, which can be relatively small near room temperature or near the temperatures you might encounter here. So the question is, what happens if this is filled up with a hot drink? So TH here is 75C. And we're going to say that the outer wall of this flask is like close to room temperature. So TC here is 25C. And there's some kind of crack in the shell. And as a result, some air gets into that gap and it'll essentially recover ambient pressure or room pressure. So for the time being, we're only going to consider conduction heat transfer through this gap from the inner to outer wall, because if it's a relatively narrow gap, we wouldn't expect there to be much convection that could develop in that narrow enclosure. So let's see if that possibility of air coming into this gap could make a significant difference on the insulation performance. So to start with, let's just consider some portion of the inner wall, which is at TH, and the outer wall here, which is at TC. And between them, we've got some heat transfer that's going through. And let's say in the first case, we're going to consider this is a perfectly sealed vacuum, so there's only radiation between the two. And the way that we're kind of approximating this is with some equivalent emissivity. So we could say that if there is a good vacuum, then the heat transfer rate would go as Q dot double prime radiation. So that's our heat flux due to radiation is just going to follow epsilon sigma TH to the fourth minus TC to the fourth. And that works out to about 116 watts per meter squared per meter squared. And make sure here that your temperatures you're using in Kelvin. And as a reminder, sigma is like 5.67 times 10 to the minus fourth watts per meter squared Kelvin to the fourth, or times 10 to the minus 8. Okay, so that would be the case for a perfect vacuum. Now let's consider what if there was also the possibility of conduction through that gap. So let's now consider that this gap also has air in it, and there's going to be conduction through the air. And this gap has a 2 millimeter space, or 2 millimeter width. We'll call that delta. So in that case, we've got now an additional mode of heat transfer through the gap due to conduction. So that is Q dot cond is equal to TH minus TC over the conduction resistance, or the areal conduction resistance through that gap, which is going to be K of air divided by delta. And here, K of air at some average temperature between the two surfaces, so let's say at about 50 C, if we look that up, that is 28 times 10 to the minus 3 watts per meter squared, or meter Kelvin. So if we plug this in, we're going to get 700 watts per meter squared heat flux due to conduction through that gap. So if we look at these two, we could observe that in this case, the conduction heat flux compared to just the radiation heat flux is like on the order of 7-fold. So essentially the insulation of this would be severely degraded because you'd have 7 times higher heat transfer than if you just had the only radiation through that vacuum gap. So let's say that this severely degrades the insulation performance of this flask. Second conceptual question. So we've got this 3-layer assembly. So we've got 3 slabs. They're all of the same thickness, but they have different thermal conductivities. A and B are both the same, but KC, the 3rd layer, is a lot less thermally conductive. So our left wall is insulated. Our right wall is at a specified temperature, and there's a positive volumetric heat source within the leftmost wall. So what we want to do now is sketch the temperature profile through these layers and work out what the important features are, or make sure to identify the important features in that profile. So just to indicate here, this is our X direction, going left to right. So let's sketch this out here. So we've got temperature on our vertical axis and position on our horizontal axis. So we'll just indicate our various layers. So we've got layer 1, let me make these a little bit more equal in thickness here. So we've got our 3 layers here. So this is A, B, and C. All right, so let's indicate a few properties here. So first of all, we know that our rightmost layer, KC, has on the right side a known temperature, which is T infinity. So let's indicate T infinity here. And we know that there's heating in the left layer where Ka is, and the left wall is insulated. So that means that all the heat has to actually flow from the right, or from the left to the right side. So that gives us an idea that the temperature inside this whole assembly is going to be higher than T infinity. Okay, so next, let's take a look at Ka. So since the left layer is insulated on the left side, it's going to have a 0 temperature derivative, or dT dx is going to have to be 0 right at the wall, right at the left wall. And also, the first layer has a heat source inside of it. So you would expect a parabolic temperature profile, which should be hottest again at the middle, and then increase in slope, or increase in slope magnitude as you work outwards to the right. So let's just indicate a couple of the interface positions here to help form this plot. So we would expect a parabolic type profile here on the left. And since layers A and B have the same thermal conductivity, the slope has to be continuous, or dT dx is going to be continuous between those 2 layers. So the other comment here is that layer 2, layer B, doesn't have any heat source, so it's going to just have a linear temperature profile. So that would follow like this. Let me adjust A to make this come out a little cleaner when I draw this. So A is going to have a parabolic profile. Let's draw it going to there. Okay, so now we've got B. So B will have a continuous slope here, and it's going to be a straight line. So this one is parabolic. This is linear. This slope here is continuous. And then Kc has a much lower thermal conductivity than Kb, but the heat flow rate, or the heat flux through C, is the same as B. So for that to work, the last layer has to have a much sharper temperature gradient, or a much greater slope. So essentially this one is also linear, but with a much greater slope than in B. And really, to be precise, we would say that in this case, because of the nature of the setup, we would say that dT dx in C is 10 times dT dx in B. Maybe not drawn quite as exaggerated in this diagram. All right, so now we're up to question 3. And here what we're looking at is the following situation. So we've got this pipe. The inner radius for this is radius R1 for our inner radius, and it has a layer of foam insulation wrapped around it with radius outer radius R2. And what we're going to say is that the outside is cooled by convection to the ambient with some heat transfer coefficient. So there's some H here, and that is for convection from that outer surface to T infinity. And we could kind of represent this conduction through this layer of insulation as a sort of two-step, or as a two-step thermal resistance network. So we could say at the inner wall of that insulation, the temperature is going to be T1, and then there's going to be some conduction through the insulation with resistance Rcon for the insulation, and that will bring us to the outer surface of the insulation. And then out here there is convection to the ambient at T infinity with convection resistance on the outside. So your normal intuition would be that you would want to put more insulation or increase the thickness of this insulation if you wanted to reduce heat loss through the system. So in other words, if we can increase the thickness of that insulation, our Rcon for the insulation goes up. And then as a result, you might think that the overall thermal conductivity or the overall thermal resistance of the system would increase and you'd have less heat loss through the insulation. However, if we increase the size of this insulation or the thickness, the outer surface area also increases, which provides more area for convection heat transfer on the outside. So the question is it possible that increasing the thickness of the insulation could actually reduce the convection resistance so much so that the overall heat transfer rate increases rather than decreases with more insulation? So let's set this up here. So our individual terms here are Rcon for the insulation. We can write that as the natural log of R2 over R1 divided by 2 pi times K of the insulation times L. And this is just me remembering a formula that we worked out in class earlier in the semester. And then for convection, we could say that this is equal to the 1 over the convection heat transfer coefficient times the surface area on the outside, which would be 2 pi times R2 times L. So our total heat transfer rate, Q dot, is equal to, let's say, T1 minus T infinity over the total thermal resistance, which is Rcon for the insulation plus R convection. So if our question is, could raising R2 increase the heat transfer rate between the pipe and the surroundings, then that means that could increasing R2 reduce the denominator of this expression. So let's just isolate the denominator here and recognize also that both of these have a factor of L that we can factor out. So in that case, we could say on a per length basis, we can write as the following. The resistance per length for this system, R prime, is equal to the conduction resistance, so natural log of R2 over R1 divided by 2 pi K of the insulation. I'll just call it K now. And then plus, for the convection, we have 1 over, let's see, H times 2 pi R2. So the question is there a point at which if we increase R2 further, this R prime actually starts to go down rather than go up as you might expect? So to test that, we could just take a derivative here. So we could just say, if I calculate dr prime dr2, we could see if there is a 0 in this, and if there is a 0, that means that there's sort of a point beyond which changing the resistance or increasing the resistance will actually flip the effect. So in other words, let's check that here. So we'll go through this term by term. So let's see. So we'll have let's see, for our first term, when we take that derivative, we can expand this out. So this is ddr2 of natural log of r2 minus natural log of r1 being a constant here, over 2 pi k. And then for our second term, this is going to be, since r2 is in the denominator there, then our derivative is just going to be minus 1 over 2 pi h r2 squared. And let's just kind of keep this going here. So if I take that derivative in the first term, we're going to get, let's see here. So I'll factor out 1 over 2 pi from both terms here. So we will get the following. We're going to get 1 over r times r2 times k minus 1 over, let's see, this is going to be 2 pi is out there, so we have r2 squared times h. Okay, so now just doing a little bit more rearrangement here. Okay, so picking this up, let's just do one more factoring step here. So we'll just factor out that r2, and we'll get 1 over 2 pi r2 is equal to, or sorry, times 1 over k minus 1 over r2 times h. So if we want to know if there's a minima or a maxima for this function, essentially, is there a value of R2 that gives us, in our case, the maximum thermal resistance, then we can look for when is dr prime dr2 0, and that will show up under the following case. So dr prime dr2 is equal to 0 when R2 is equal to k over h. So in this case, if we plug in R2 equals k over h here, this will give us a 0 slope. Now that we recognize that there is this local minimum or maximum that exists, now we should ask, what does this actually mean? So or what does this actually imply? So let's just sketch this out and see what this suggests for us. So if we draw here the overall thermal resistance through the insulation and the convection on the outside, and we'll draw here R2. So R2 can't be less than R1, otherwise it would be kind of inside out. And somewhere in the middle, we have R2 is equal to k over h. So let's just ask what happens if R2 is less than k over h. So in other words, we're on the left-hand side of that curve. So if R2 is less than k over h, then that means that the denominator of this second term is going to be smaller than the first term. So therefore, the magnitude of the second term will be greater than the first term, so you'll have a negative number. So that means that here you would have a negative slope, or in other words, r is going to be decreasing up to this point, and then beyond that r is going to be increasing. So in other words, if you have too thin of a layer of insulation, so in other words, if R2 is if R1 is sort of or R2 is small to begin with, and you increase that a little bit, you'll actually increase the overall heat transfer rate. But then once you go beyond this threshold, increasing R2 will just increase the overall insulation or overall thermal resistance. So what we conclude is that increasing R2 beyond some limit, beyond k over h, will always increase the total thermal resistance, or therefore always reduce the thermal heat always reduce the heat transfer rate. But if you start off with a very thin value of R2 and you increase the thickness of the insulation a bit, you could actually temporarily decrease heat transfer performance or increase the heat loss rate in this relatively narrow band of conditions. So you would want to make sure that your insulation is always at least thicker than that, but you don't really ever have to worry about over-insulating like the problem poses. So next up, we've got this interesting conceptual question, which is asking why when you look at many heat sinks, the fin profile is actually triangular rather than squared off. So the question is, why would you do that? Why would you make this thinner as you get further away from the base rather than have a constant cross-section? So this question, it's getting a little bit more qualitative than some of the previous ones, but the basic idea is that in a fin, as you go up away from the base, if there's some heat transfer rate going into the base, let's just imagine there's heat transfer to the surroundings, then the amount of heat transfer going through each subsequent cross-section is going to be decreasing. So in other words, the conduction heat flow rate decreases as you work your way up or along the fin. So since there's less conduction heat transfer as you move further away from the base, there's less need for that larger cross-section to allow very low resistance conduction heat transfer because there's less heat flux trying to move through each subsequent layer. So another way of posing this is that for a given amount of material, let's say you've got a certain mass of material and you're trying to sort of design an optimal fin that's going to have the highest efficiency, if you recognize that the greatest heat flux has to move through the base and there's very little that needs to flow through the tip, if you were to just sort of reform that fin or redistribute the material in the fin into something like this, so essentially imagine these two had the same areas in the cross-section, this triangular fin would have more cross-sectional area where there is a higher heat flow rate. So where the heat flow rate is greater. So as a result, it'll sort of be overall more efficient, or essentially this sort of wedge at the top of the sort of rectangular or square fin will be sort of extraneous, that there will be extra area for heat transfer where there's very little heat flow. So it'd be sort of oversized up there. So that's really all there is to this question here. Okay, one more fun conceptual question to look at. So here's the story. We've got a steak that's being cooked on a grill or in an oven, and we've got, imagine that there is heat coming in from the top and the bottom, and our question is, first question is, how is the temperature profile through the thickness going to vary during cooking? And I know I said top and bottom, but just for the sake of argument, let's draw this on the x-axis here. So imagine this is the steak here, and it's got some thickness. So let's say that it has width W, or in other words, there's W over 2 on either side of that. So we've got heat coming in on both sides, or essentially we're heating this maybe more reasonably like convectively with like some T infinity, which is greater than T of the steak here, or we'll just call that T. So here's what we might expect to occur during the cooking process. So let's sketch this out here. Okay, so during cooking, if we were to draw the temperature profile here, so here is X, here is T, we'll draw up here T W over 2, and then we've got over here negative W over 2. So initially, at the start of our process, our steak, right when we put it into the grill or oven, it's going to be at a uniform temperature. So let's just call this TI. So initially, once we start cooking, we're just going to sort of start heating up the outside surface. So we'll just have a region near the outside surface that is starting to get heated, and then that wave or that thermal penetration depth will get greater, and then it'll get, eventually it'll sort of work its way all the way through this thickness. And since we have a fixed T infinity, the outer edge will never exceed or quite reach T infinity, but it'll start getting closer and closer, and the slope through the middle will kind of shallow off, but you're always going to be symmetric around the center line. So we would typically make an indication that this is the direction of time. Okay, so then there's this note, if you read recipes, that you should actually allow a steak to rest for a few minutes after you cook it, before you serve it. And that has to do with this sort of dip in the temperature profile shown there. So if we now kind of think about what happens once we're cooling this, so now we've got a sort of flipped situation. So now we have temperature T pointing up, and we'll draw our x-axis as before. So this is W over 2, and this is minus W over 2. And we're going to start off, and now our ambient temperature is below the steak temperature. This is like room temperature now. Okay, so we're going to initialize our process now, not with a uniform temperature anymore, but the final temperature that we had from the cooking process that, sort of might look like this. This sort of, symmetric profile here. That's cooler in the middle and hotter at the surface. So what's going to happen is that once we let this sit at the room temperature, the outside is still hotter than the middle. So the middle will actually start to come up in temperature a bit. So you'll see that there's going to be a little bump up in the middle, but the outside surface might start to cool down a bit. So the colder parts of this will get hotter, the hotter parts will get colder, and you might see, after a little time, maybe something like the following. And then this is still got to be a symmetry condition, so you're still going to have something like this in the middle. And then if you allow this to go a little further, your outside might get a little colder, but then your inside might kind of still work its way up. And the basic idea here is that by doing this, we're going to make sure that this is cooked all the way through. So in other words, if we kept it in the oven, we might risk burning the outside, which we don't want. So by doing this, we're sort of allowing the sort of remaining temperature or higher temperature near the surface to do the rest of the cooking for us, rather than keeping it in the oven too long and cooking this all the way through. So you'll kind of have like a little bit of a weird flip happening here, where the inner temperature is coming up, but the outer temperature is going down, and this is going to get more evenly cooked throughout. Now let's get on to the meat and potatoes of this exam or practice quiz and start looking at the full worked questions. So first we're going to look at this so-called multi-mission radio type thermal generator, MMRTG, classic NASA acronym. And this is set up to basically be this cylindrical radioisotope unit. So basically this cylindrical billet of metal or ceramic that's going to generate heat, and it's stored in a vacuum gap inside this enclosure. So the ceramic cylinder is going to generate heat at a certain rate, and it has some material properties, and there's a surrounding enclosure, and we're modeling the heat transfer from the outer surface to this enclosure here essentially as radiation. So these aren't in direct contact, there's a gap, and there's some radiation with sort of an effective equivalent emissivity of epsilon is 0.8. And for now, we're going to ignore the top and bottom faces of this and just think about this as a cylinder that's, very long such that the end effects at the top and bottom are not significant. All right, so given that, the equivalent diagram is shown here. So our top and bottom surfaces are insulated. We have some volumetric heat source inside, an outer radius. R is our radial coordinate, and then Tc is the temperature of that enclosure, and there's some radiation in this gap with some equivalent emissivity. So let's pick this up here. We're going to set up the conduction equation for this domain. So this is a cylindrical domain. So let's write out our conduction equation for cylindrical coordinates. So we've got the following equation here. So let's see, on the left we're going to have the transient term, or the energy storage term. So we'll have rho Cp d temperature d time. And since we're working in cylindrical coordinates, since our geometry is cylindrical, we can write this as the conduction term or diffusion term in cylindrical coordinates. So we'll have the following: 1 over r ddr of kr dt dr plus 1 over r squared dd theta of k dt d theta plus ddz of k dt dz. And here we actually have a heat source inside our domain that we need to consider. So we have plus this volumetric heat source due to the radioactive decay of this isotope. Okay, so now let's step through and simplify this equation. So we're going to say that it's a steady state problem, so our ddt term drops off. We'll say that it's axisymmetric, so that means that there's no variation in the azimuth, or in other words, dd theta is 0. We said that there's no end effects, and we're treating this as a long cylinder, so there's no variation in the z direction. So let's now kind of reduce this equation to the remaining terms. So we have the following. We're going to have 1 over r ddr, and since this is now only a function of r is our only variable left, we can write this as a regular derivative, not just as a partial derivative, of kr dt dr, and that's going to equal minus q dot triple prime. So that's our governing equation, and our domain that we're considering is from r equals 0 to the outer radius of the cylinder, which we're going to call big R. So it's a second order differential equation. We have two boundary conditions, so we need to specify our BCs. So our first one, BC1, is at r equals 0. And here, since this is a cylindrical coordinate problem, we know that if r equals 0 is inside the domain, we're going to have a special rule at that center axis, which is that temperature is bounded at r equals 0. So that's our first BC, which is a little bit of a funny one. It basically just means that we know that when we solve this equation, we're going to get like a natural log of r term in there and multiply it by a constant. And for that to not blow up, to keep our temperature bounded, we need that constant t equals 0. Okay, so our second boundary condition is going to be at the outer edge. And here we've got the following. So consider now the outer edge of our cylinder here. So we've got some conduction going into this, a conduction heat flux at R, and that's going to have to equal the radiation heat flux going from that outer surface to the surrounding shell, which is at Tc. So the way that we could write this is that if this is the radial direction r, we could say that the outward heat flux at the outer perimeter of this billet of plutonium oxide or something is going to be minus k, well, regular derivative dt dr, evaluated at the outer radius, so evaluated at big R, has to equal the radiation heat flux to the surroundings. So that's epsilon sigma, the temperature T of R to the fourth minus T of the surroundings, Tc to the fourth. And those again have to be in Kelvin. Okay, so now we've got both of our boundary conditions and we've got our reduced governing equation. So now everybody's favorite step here is to solve out that ODE. So we're going to solve that conduction equation, plug in our boundary equations, and work out the temperature profile in that domain and sort of evaluate the values at the inside and outside. Okay, so let's start here with our reduced equation. We have 1 over R ddr of kr dtdr, and that is equal to minus q dot triple prime. So we'll bring the R factor over to the other side here, and then we'll integrate both sides of this dr. So when we integrate the left-hand side, we're just going to sort of undo the derivative term in front. So we get the integral of ddr of something dr. We just get the argument of that. So that's going to be kr dtdr. And then on the right-hand side, we're going to integrate a constant times r dr. So we'll get minus q dot triple prime r squared over 2. And then there's a constant of integration that comes out. Next, we'll divide by kr. So we'll get dt dr is equal to minus q dot triple prime r over 2 plus c1 over r. And then, c1 over kr. And this first one here has k as well in the denominator. Can't forget k. Okay, and just as a note here, we haven't really defined yet what C1 is, and K is just a material property, it's a constant. So we can essentially just roll that up into C1 and just say C1 is not yet worked out, but if we need to work it out at some point, K will sort of come out there because it can just be any constant. So we don't really need to worry about the K there. Okay, so finally, we're going to integrate both sides, again with dr. And we do this, and now we're going to get the last temperature equation here. So we'll get T of R now is equal to, when we integrate the negative q dot triple prime r over 2k, we're going to get minus q dot triple prime r squared over 4k. The c1 over r is going to become c1 times natural log of r. And then finally we have one more constant of integration. We'll call that C2. Okay, so now we can apply our boundary conditions here. So BC1 is that our temperature is bounded at R equals 0. So T of R equals 0 is finite. And that can only work if this term here, C1 natural log of R, is finite at R equals 0. So for this to work, C1 has to be 0, otherwise you'd have natural log of 0 or a negative infinity in your solution. So we could conclude that C1 has to be equal to 0. Okay, so for our second boundary condition, now evaluated at the outer radius, we have, we can plug in our solution here. So we have minus k dt dr at big R, and that is equal to epsilon sigma T of big R to the fourth minus T infinity to the fourth. So we'll take our derivative here. So the C2 drops out when we take that derivative because it's a constant. So we're going to get minus K times Q dot triple prime, negative Q dot triple prime, big R, and there's a factor of 2 that comes out, so we'll get that over 2K, and that should be equal to epsilon sigma. Okay, so now we have temperature to the fourth power. So we could plug that in at R. So we're now going to get, let's see here, C2 minus Q dot triple prime big R squared over 4K, and this group to the fourth power minus T infinity to the fourth power. Now we've got this form, so we just need to solve for C2. So let's just say some algebra magic happens and skip ahead. And we will get the following result, that C2 is equal to the following. You get Q dot triple prime R over 2 epsilon sigma plus TC to the fourth, that to the 1/4 power, plus Q dot triple prime R squared over 4K. So now we will take this and plug it in for C2 up here, and we will get the following general form for the temperature profile. We will get T is equal to Q dot triple prime over 4K big R squared minus little r squared, plus this group here, Q dot triple prime R over 2 epsilon sigma, plus TC to the fourth, and all that to the 1/4 power. So that's our specific solution here. So essentially what we've got is a parabolic profile in R. So if we want to plot this here, we know that it's going to be the highest temperature in the middle, and then as the local coordinate r squared gets bigger, this first term gets smaller, and then we approach the quantity on the right. So we will have our temperature here, and we're going to have our coordinate here, and then this is R. So out here we're going to have the heat sink temperature Tc, and then at the center we're going to have our hottest temperature, so that's T of R equals 0, and then we're essentially going to have this parabolic profile that decays out to some value out here. So our lowest temperature is going to be at the outer edge of this domain. So we can plug that in here. So at this particular point at the outer radius, we'll have 1219 Kelvin. And then at the center, we're going to have the highest temperature, which is 1339 Kelvin. Okay, so, well, we actually kind of did the following step here. So we generated this plot. This is, zero slope, or kind of like an adiabatic central axis condition here. And, this is 1219 Kelvin, which is just a little higher than the heatsink temperature of 1200. Okay, next. We've got the upper limit is that the RHU ceramic will sort of break down above 1200 Kelvin. So if you make this larger, you're going to expect that the inside will get hotter and hotter. So the question is, how large can you make this, or how big can you make R before this breaks? So we know that the hottest point will always be in the middle, so we could essentially set up our equation as follows. We could say that T of R is equal to 0 is equal to T max of, which is 2000 Kelvin. And that's going to equal the following. It's going to be equal to the temperature evaluated at R equals 0. So that becomes, plugging R equals 0 into our formula here, we have Q dot triple prime over 4K times our R squared plus q dot triple prime r over 2 epsilon sigma plus tc to the fourth, and all of that to the 1/4 power. And what we'll do is we'll solve for r in this case, such that, you know, this whole group on the right hand side equals 2000 Kelvin. You could do this by trial and error. Wouldn't recommend. I'm not sure if it's feasible to actually solve this directly given the form of the problem. You could, you know, plug this into EDS. But when we do this, we're going to find that this R that will give us T max is going to come out with as like R is equal to 0.20 meters. So that's sort of the upper limit. If you made it even thicker than that or larger in radius, then the core would get hotter than the upper working limit of that material. Next question. We're looking at this cooling system for a car with a turbocharger in it. So we've got a turbo compressor, and that's essentially increasing the pressure and density of the air that's going into the engine in a car. And what you're often going to have is a intercooler or a heat exchanger that's going to cool down that air a little bit before it reaches the actual engine intake. So the idea is that if this intercooler is working correctly, it should bring the compressed air temperature down to about 50 C right before it goes into the actual engine. So coming out of the compressor stage and basically on its way to the intercooler, the air might be at 150 C, for example. So there are companies that sell these things that they're calling pre-intercooler pipes, which are these like finned pipes that you would put between your compressor and your intercooler to give you a little boost in cooling capacity to help bring down that air temperature. And let's just say the geometry of one of these is as follows. It's like 43 millimeter inner diameter pipe. The outer diameter of the tube is like 51 millimeters. It's like a little, like around 9 inches long. It's got hot air flowing through the inside with a heat transfer coefficient associated with it. A bunch of these longitudinal fins on the outside. And here are some geometry properties for that. And then there's convection on the outside of that. And we want to see if this actually makes a meaningful difference to the performance of the system. In other words, does this add a significant amount of cooling capacity, or is it just kind of, eye candy and it's just kind of a scam? So to start off with, let's think about a thermal resistance network for the hot air flowing through this intercooler or pre-intercooler pipe, and the thermal resistance from that to the surrounding ambient air. So we've got a couple stages here. So let's sketch this out. We've got this pipe here, and there's going to be conduction through the wall of this pipe. So we've got hot air on the inside. There's the inside of that pipe wall, the outside of the pipe wall, and then there are these fins that are sticking out radially from this. And from there, there's convection to the ambient. We're calling that T infinity. And we want to work through this. So to start with, our resistance network, it's going to begin, let's say, in the center. So we'll have convection from the air flowing through this pipe to the inside wall of the tube, or of the pipe here. So we'll call this Ti. So we'll say that there is going from Th to Ti, and between that, there is an internal convection resistance. Let's call that Rconv I. And then we've got conduction through the pipe, which is essentially an annulus. So that'll take us to, we'll call this point here TO. And then we have these fins sticking out, and we combine the conduction and the convection from those fins in a single fin resistance stage. So then this goes to T infinity out here, and we've got our fins here, and we've got our cond here. So we've got those three stages. The next step in this analysis is to step through all the individual resistances, calculate them, and work out the overall thermal resistance through this network. So we'll start with the convection resistance on the inside of the pipe. So we'll call that Rconv I. And this one is pretty straightforward. It's just going to be 1 over the heat transfer coefficient on the inside times the surface area on the inside of that pipe. So that's pi times ID times the length. And this works out to 0.184 K per watt. Next, we have the conduction through the annulus, basically from the inside wall to the outside wall of this pre-intercooler pipe. So that one is just, again, a formula that we've used a few times already. So we'll do this as Rcond. Let's see, what do we call it here? We called it just Rcond. That's fine. So that's equal to natural log of the OD divided by the ID of that pipe over 2 pi KL, where K here will look up a value, assume that this is made out of aluminum, and if it's going to be at a higher temperature, it might have some thermal conductivity. Let's just say that K for aluminum is about 150 watts per meter Kelvin for some highly alloyed aluminum that you might use here, like a 6061 or a 7000 series or something like that. So that comes out to a relatively low thermal conductivity. So even if, or low thermal resistance, so even if our thermal conductivity guess was off, it wouldn't affect the overall resistance much. This is going to be like 0.79 times 10 to the minus 3 K per watt. So pretty minimal thermal resistance in the overall scheme of things. Okay, so next we have to look at the fin resistance. So this has a couple steps to it. So let's start going through those. So first of all, we want to work out the resistance for an individual fin coming off the outside surface of this pipe. So this is a longitudinal fin. It's got a rectangular profile. So even though it's coming out radially, we can treat it as if it's just a regular rectangular fin. So we could say that for an individual rectangular fin, so that fin has length L here, and it has a parameter M, where M is defined as the square root of 2 times the heat transfer coefficient. So we're calling, this heat transfer coefficient on the outside, we were calling that HO to T infinity. So we have 2HO over, again, the thermal conductivity of the aluminum and the thickness of the fin, where T fin is this thickness here. And we can just calculate this. This comes out to like 21.1 over meters. And we can plug that into the single fin efficiency formula for a rectangular profile fin, which is eta of a single fin of this form, just rectangular fin, is going to be hyperbolic tangent of m times L over m times L, and this comes out to 0.97. So this is a relatively thick fin, and it doesn't have an extremely high convection coefficient on the outside, and it's made out of aluminum. So for these reasons, you might expect a relatively high efficiency. So next step is we need to work out the overall surface efficiency, which accounts for both the fins coming off this tube, as well as the bare surface area that doesn't have any sort of conductive loss through a fin. It's just directly cooled by the convection. So to do that, we need to calculate a few geometric parameters. So let's just step through these. So first of all, we could say for each fin, so each individual fin, it's going to be equal to 2 times the length of the pipe in the flow direction times the length of each individual fin. So essentially these are rectangles and we're not accounting for the ends or the tips, so we're just approximating it as, a two-sided rectangle that is, we said like 200 some millimeters long, and these individual fins are coming off a bit. So that for each fin is going to be 0.00598 meters squared. We have the base area, which is the area of the outside surface of that cylinder that's not covered by the fins. So that's going to be equal to the outside surface area of that cylinder, so pi times OD times L, minus the portion of that that's covered by the fins. So we have some number of fins, and they're going to cover individually strips that are T fin wide by L long. So this gives us a uncovered base area of 0.00235 meters squared. And from there we can calculate also the total area, which is just AB plus the number of fins times the area of the fin, so that comes out to 0.3014 meters squared. So now we can plug this in for the correction formula that gives us the overall efficiency for the surface, including both the fins and the bare exposed tube area. So we could say that the overall efficiency of the surface is going to be 1 minus number of fins times the area of each fin over the total area times 1 minus the efficiency of a fin, and this comes out to 0.97. Just barely, if you go to additional decimal places, you'll see it's very slightly higher than the efficiency for a single fin, but not much more. So once we have that, then we can say that the total fin resistance, which includes both the convection on the outside of the fin, the conduction through the fins, and the directly convectively cooled base area, is just now going to be 1 over eta O, the overall surface efficiency, times HO times the total area of that fin surface. So that comes out to 0.0342 K per watt. So finally we can get our net efficiency, which is going to be our net resistance, which is the sum of those three individual resistances. So R net is equal to R conv I plus R cond through the tube wall, and then the fins on the outside. And let's see, so this total resistance is going to be 0.219 K per watt. Okay, so next we want to estimate the heat transfer rate from the pre-intercooler pipe to the surrounding air. So in this case, we've got, if we don't consider the temperature variation of the air going through the pipe, we could just say that that heat transfer rate is going to be, if this is the pre-intercooler pipe, let's say, and we've got the air coming in at TH, and there are these fins on the outside of this pipe, and there's some Q dot going to the surrounding air at T infinity. We could say that the Q dot is just going to be, at the most, at least, we could say it's TH minus T infinity over that R net. And here that works out to 571 watts. So the question now is that a large heat transfer rate or a relatively insignificant one compared to what the overall intercooler system has to do? So recall that we have this pre-intercooler that you would install upstream of the main intercooler, and the question is, does this help much, or is it just sort of a scam or not something so valuable? So let's just look at what the overall intercooler has to do. So ignoring the pre-intercooler, we have that air coming in at TH. It's going through this larger heat exchanger, and that's getting rid of some heat. We'll call this Q total. And it's got to come out at TC, where we said TC was 50C, TH is 150C. And we said up here that M dot for this system is 0.15 kilograms per second. So when we plug that in, we get that Q total ought to be M dot CP TH minus TC. M dot is 0.15 kilograms per second. Let's say specific heat of air is about 1020 joules per kilogram K, depending on the exact temperature, but let's just approximate it there. And then we have a delta T of 100 degrees. So when we put that in, we get our total Q is about 15.3 kilowatts. So the pre-cooler just provided, 500 some kilowatts, so really just a couple percent of the total heat load. So our conclusion here is that this pre-intercooler pipe doesn't really do much. In other words, it's only going to get you like a couple percent of the way towards the total amount of heat transfer you need to achieve in this intercooler. So this pre-intercooler pipe really isn't worth it, I would argue in general. Just put a regular pipe there, don't worry about it. Home stretch here, last problem to work through. We're looking at this kind of funky problem where we've got this cylindrical tank full of water, and we're using that to store heat that you might have, left over for some process, or you're trying to, build up a lot of hot water when you've got low price of electricity or something going on like that. So there's hot fluid flowing through this jacket that's sort of wrapped around this cylinder, and that's essentially convectively heating the water on the inside. So essentially we have some kind of heat transfer coefficient here. H is 200 watts per meter squared K. We have our outer dimensions of the tank itself. So it's 1 meter in radius, 3 meters tall. The tank is initially filled with water, and we're going to pretend now that there's no flow in there. So there's no natural convection that develops. This is just a conduction problem and a transient conduction problem. We now have enough information here. So now here's the idea. So we're going to heat up this tank of water by running hot fluid through that jacket for 4 hours. And this is a transient heat transfer problem. We want to try to start by working out what is the right method to choose to model this transient heat transfer process. So to begin with, let's see if we can get away with lumped capacitance method. So that would be the simplest one if it were to work. So what we could say with the lumped capacitance method is that so our Biot number for the lumped capacitance method that we would use to check is defined as h times the length scale. So for this geometry, that's going to be the outer radius over 2, since it's a cylinder, over the thermal conductivity of the water. So for water, this is like 0.65 watts per meter Kelvin or so. H was 200 from the problem. Let's round this down to 0.6. 0.65 might be more representative of the hot water. So when we plug that in, we're going to get a Biot number based on this of like 167, which is clearly much greater than the threshold we would use for the lumped capacitance method of 0.1. So this is unfortunately not okay for lumped capacitance. So now we've got to find our next option. So next we could check, can we use a first term solution or first term of a series solution for this sort of domain? So we can see if the first term series solution would work. And to do that, we would evaluate the Fourier number. So here we've got the Fourier number FO, and that's defined as alpha times t times the radius here squared. And when we plug that in, alpha for water is like, let's say 1.43 times 10 to the minus 7 meters squared per second. So when we plug that in, we'll get the Fourier number is 0.002, and that is not less than our normal threshold of when it's safe to use just the first term. So in other words, what's going on here is that we have a sharp temperature variation through the domain because the Biot number is large, and also the Fourier number is small, which means that our conduction process in this region has really only reached the sort of very close to the wall region of this tank. It hasn't really penetrated through. So what that tells us is that this is essentially just like the start of a conduction to a very large domain, or essentially this is a semi-infinite domain problem. And another way that we could sort of verify that that is the case is if we were to check for the thermal penetration depth of a wave kind of coming in from the surface going into the thermal penetration of a conductive front moving in from the surface during that 4-hour period. So we could see just what is our penetration depth here as another way of verifying this. So we could say that delta P is like 2.1 times the square root of alpha thermal diffusivity times the time of this process, T. And that works out to just like 0.1 meters. So in other words, this is a 2-meter diameter tank, but the thermal wave has really only penetrated 0.1 meter in on either on anywhere around the exterior of this tank into the bulk of the water. So this is really just in the startup phase. Essentially, it's a semi-infinite problem. So that tells us how to do it. Now let's sketch out the temperature profile that we would expect through this tank during this heating period. So we'll draw the R-axis here, our temperature axis up here. We have our tank is initially at temperature Ti, and it's being heated by this hot coupling fluid at temperature Th. And we'll just indicate here, this is RO and this is RO. So initially, our water is all at temperature Ti at the very start of this process. And once we start the heating, we're going to get this region that's essentially locally heated near the wall. And since it's sort of effectively a convective process, this temperature won't shoot up all the way to TH. It'll get close and it'll sort of incrementally get closer, but because of just the ratios of this problem, this temperature profile is, going to be pretty steep, right near the edge, and it's going to get almost all the way up to TH pretty quickly. And then over time, this will, essentially start penetrating a little further into that tank of water. And it's going to get a little closer to TH at the two limits, or at the two edges. But it's never going to have penetrated all the way through that tank of water during the 4-hour period. It's only going to be sort of near the edges. And although, the way that we've drawn it is maybe exaggerated, this thickness, as noted above, the penetration depth is only like, 10% of RO. So it's a little exaggerated here. And just to, indicate clearly, we're saying that as these curves, sort of work their way up, time is advancing. Okay, next step here. So now what we want to do is we want to work out the total rate of heat transfer to the water after 4 hours, and essentially the resulting increase in the average temperature of the water. So there's a hint here which says that for the situation in question, high Biot number, low Fourier number, we can argue that the surface temperature at RO, so essentially T of RO, while it's technically changing in time, it's almost approximately equal to TH. So then we can use a solution that was listed in the class notes in the textbook for the transient heat flux for the case of, so the transient heat flux at the surface for a semi-infinite problem with a constant wall temperature. So with a constant T wall. So the instantaneous heat flux from that formula is going to equal the following. So that's the heat flux at the wall is from that formula K times the coupling fluid the surrounding or the wall temperature, which is TH, minus the initial temperature TI, over square root of pi times alpha times T, the total heat in, Q. So that would be the integral from T equals 0 to the end of this process. So that's going to be 4 hours, or we'll just call that TF, times the surface area of the outside of that cylinder AS, times the instantaneous heat flux, Q dot double prime of T, d time. So we can just rearrange this a little bit, factor out some of the common terms here. So we have KTH minus TI over square root of pi times alpha. And then we'll have the integral from 0 to the end of this process of dt over square root of t. This is going to be as follows. This will work out to as times k th minus ti over square root of pi alpha. And then we'll take that integral, so we'll have a 1/2 times t to the 1/2 evaluated from at 0, or the difference from 0 to the end of our process, TF. So we can plug that in. So we'll get that factor of 2 over there. Or I'm sorry, there's a factor of 2 like this. Okay, so we plug that in, so we get 2k th minus ti times the time of this process over square root of pi times alpha. And note that AS is equal to 2 pi RO times L, which is 18.9 meters squared. So we can plug that in, and we will get a total heat input of 2.42 times 10 to the 8th joules, which certainly sounds like a lot of joules. Okay, and then if we want to know the total average change in the water temperature, we could say that, let's say the average change in the water temperature is going to equal that total heat input, Q, over M of the water, Cp. So this is equal to Q over density of water times the volume of that tank. So that's going to be pi RO squared times the height of that tank, or L, times Cp for water. So when we plug this in, we're going to get a total temperature change of about 6.14 Kelvin on average. Although in truth, it's really mostly just the water near the outer surface. But if you then let that tank sit for a while and reach equilibrium, the total temperature should come up by about that 6 degrees. Okay, so now there's this idea to say, what if instead of just running this for 4 hours straight, what if you have this mixer that periodically takes whatever condition the water's at after a certain amount of time, stirs it so it's reaching a new equilibrium, and then we continue the process. So the idea is that in the first hour, we're running like we did before. So essentially in hour 1, our process is going to proceed like it did previously. So we're going to sort of use the same formula as above, but just plug in 1 hour instead of 4 hours. And we're going to get in that first hour a value of Q for hour 1 is just going to be like 1.21 times 10 to the 8th joules. And then we can plug in our same formula for the delta T in that first hour. And then since this is going to be well mixed, that delta T will actually be uniform throughout the tank. So that comes out to 3.1 Kelvin. So now we could say for hour 2, since we've mixed this tank, the temperature is now uniform again. And it's uniform not at the temperature that was at the very beginning of the process of 20 C. So now our initial temperature for the second hour is not 20 C, but it's now become 23.1 C because of that 3.1 K difference. So we could plug this formula in yet again, essentially we'll get a Q value for the second hour. So Q2 is going to be 1.149 times 10 to the 8th joules. So you can note that this is slightly less than the Q you got in the first hour because now the water's a little warmer and the delta T between the water and the heating fluid is a little smaller. So this gives us a delta T in the second hour of 2.9 K. And you can basically iterate this for hour, and then essentially we can work out our starting temperature for the third hour. So in the third hour, we're now up to TI for the third hour, essentially, is going to start at 26 C, essentially. So we can iterate this through for 4 hours. And what we're going to find is that after the fourth hour, so now at the end of hour 4, we're going to get the final temperature, let's say. The temperature is now going to work out to 31.38 Celsius. Or essentially the total delta T is for this 4-hour process where we're mixing after each hour is now going to be 11.38 Kelvin. So if we compare this with our result earlier, we have almost double the temperature lift over this process, which is kind of interesting. And it's again because we're mixing the water throughout the tank. So instead of having, a very small temperature difference right at the outer edge where that water is sort of being heated by the surrounding fluid, we're going to remix it and sort of reset that temperature to a lower value and sort of reheat this film region near the wall each time rather than just running this sort of slow moving process. Okay, so here's the bonus question. So if you stuck around this long, you deserve the answer. So here, the question is, what is the average temperature rise if the mixing is performed continuously? So an interesting observation is that if the mixing is continuous, then we're essentially arguing that the temperature, even though it's even though the conduction rate isn't fast enough to achieve lump capacitance on its own, this is essentially mixing the temperature throughout the tank and giving us a nearly uniform temperature. So if the temperature is uniform through the tank, then we could argue that this would be described by the lumped capacitance method. So even though the Biot number, as we normally would define it, is too large, because this is mixed, it has a uniform temperature, not because of the conduction process describing the Biot number, but just because of the mixing process that we're adding on top of it. And in that case, we can use our result from the lumped capacitance method, which is to say that, following the lumped capacitance formula, the temperature change, so TF minus the hot heat source temperature minus over TI minus the hot source temperature, should just follow exponential of minus H times the surface area times the final temperature, so that's 4 hours in, so 4 times 3,600 seconds over MCP. So we could just work this through, and we will get that the result for the final temperature would be, in this case, 64.9 Celsius, or essentially the delta T for this whole process would be 44.9 Kelvin. So that just kind of illustrates how this mixing process can really enhance the heat transfer, versus if you didn't have any flow and you were just relying on conduction alone, you would expect maybe only an eighth of that temperature difference, or seventh, or something on that order. Okay, so I hope you've found this helpful. I'll catch up with you all soon in class. Good luck in prepping for the quiz.